Well, good morning, everyone, or good afternoon, or good night, depending on when you watch this. I'm recording this in the morning, so I will say good morning and welcome to Contemporary Math. This is 3.4 Logically Equivalent Statements. So, equivalent statements. Two statements are equivalent, and we write it like this. So, it's going to be one statement and then kind of this equal sign with arrows, and then another statement. If both statements have exactly the same truth values in the answer columns of the truth tables. So when all is said and done, we get the exact same answers in the answer columns. So one way we can do this is by actually making the truth tables to show that two statements are equivalent. So here we have P or Q or R, and here we have P or Q or R. So you can see all we've done here is move these parentheses, almost like the associative property for addition and multiplication. So let's see if that matters in logic. So again, let's go ahead and write out our cases. So we get 4 trues and 4 falses. Then we have alternating 2 trues and 2 falses. And then for R, we're going to alternate true and false. Okay, so for our truth table for the one on the left, we're going to go P or, and then in parentheses Q or R. And the one on the right will be P or Q in parentheses or R. So since we have a bunch of simple statements here, we can go ahead and just copy their truth values from the cases right over here. So P was 4 trues and 4 falses. Q alternates trues, 2 trues and 2 falses. R alternates trues and falses. Okay, now we're going to deal with the or right here in parentheses. Now, or, remember the presence of true makes it true. So presence of true makes it true. So here, one or the other or both are true. In this case, the presence of true is not there, so this is a false. Here we have true, true, true. Here, there is no true, so we get false. We're going to go with this idea of this column is now the answer to this parentheses right here. Now, to see if this is an equivalent statement, we also need to fill out its truth table, and we're going to compare the answers. So fill out our P, which is 4 trues and 4 falses. Our Q is 2 trues, 2 false, 2 true, 2 false. And the R is going to alternate true, false. Okay. Again, we have to do our parentheses first with or. So the presence of true makes it true. So one or the other, or both. Here, false and false. That's the only time an or becomes false. Okay, so here we have our or column. And we are going to match that up now with the R using this or. So true or true is true, true or false is true, true or true is true, true or false is true, true or true is true, true or false is true, false or true is true, false or false is false. So our final answer then is right here. Now let's go ahead and compare the two. So we're going to compare this column right here and this column right here. Are they the same? So this one is all trues except a false here at the end. This one is all trues except for a false at the end. So because their truth values are the same in every case, we say that these statements are equivalent. Okay, and this is how you would show that. All right, moving on. It says determine whether the following statements are equivalent. So A, if you study and go to sleep by 11 p.m., then you will get an A on the test. B, if you don't study or don't go to sleep by 11 p.m., then you will not get an A on the test. So just by reading those, it's very hard to see if they mean the same thing. And so we are going to have to do our truth tables to see if they work out. So first, let's change letter A into symbols, where P is you study, Q is you go to sleep by 11 p.m., R is you will get an A on the test. Okay, so the first one, if you study and go to sleep by 11 p.m. So that's going to be P and Q. And there's a comma. Then we have the word then. So we'll put our arrow there for conditional. You will get an A on the test. So that is going to be R. For letter B, if you don't study or don't go to sleep by 11 p.m., comma, so you don't study or you don't go to sleep by 11 p.m., then, so we get our arrow, you will not get an A on the test. Okay, so you can see the structure is kind of similar, but we're not sure if these are equivalent. So we're going to take a look at the truth tables now. So instead of just writing your cases over here, sometimes you can just write them in the truth table themselves. So P was 4 trues and 4 falses. Q was 2 trues and 2 falses. And then remember, and they both have to equal true. So true and true is true, true and true is true, true and false is a false, true and false is false. Okay, false and anything is going to be false. So again, for the and, true and true is the only time you can get true. Okay. So now this and column is the only one that's left alive, and it's the answer to your parentheses. Let's go ahead and fill out column R. So this is just alternating. Okay, so now we're going to compare this column with this column. We're going to do it using a conditional. So for conditional, Remember, the only time that it's false is this one. Okay, so if true, then false. That's our only false. Otherwise, it has to be true. So here, T arrow T is true. If true, then false. That's our only false case. If false, then true. That has to be true. And as we talked about last time, if a conditional starts with a false, it automatically becomes a true statement. So we could save ourselves a little time just by looking here at the beginning of that conditional. The antecedent, when it's false, equals true. Okay, so we have this as our final answer. So what we're going to go ahead and do is find this truth table. So here we have not P or not Q. So not P is just going to be the reverse of P. So we get 4 falses and then 4 trues. Not Q is going to be the opposite of Q. So we're going to get 2 falses alternating with 2 trues. And then we're going to combine this with or. So the presence of true makes it true. Okay, and then not R is going to alternate in reverse of R. So it's going to be false, true, false, true, false, true, false, true. And then we're going to compare these 2 columns with our conditional. So again, the only time it's false is if true, then false. So if false, then false is true. If false, then true is true. If true, then false is false. If true, then true, that's true. If true, then false is false. If true, then true is true. If true, then false, that's false. And if true, then true, that's true. So this is our final answer of this truth table here. And if we compare the ones in blue, here we have true, false, and then all trues. Here we have true, true, false, true. So you can see that the truth tables do not match. Therefore, these statements are not equivalent. So what if we don't want to spend all that time taking a look at the truth tables? It can be a little bit tedious. There are some laws that we can begin to apply to tell whether statements are equivalent or not. And so one of those laws is De Morgan's laws, just like in set theory. So you'll recall in set theory, if we had something like A union B complement, that was the same thing as A complement intersects B complement. And we said, well, go ahead and just take that complement and sort of distribute it in here and switch everything. So the same thing's going to happen for our logic. So if we have the negation of P or Q, notice that's pretty much the same thing here. A union B is P or Q. Complement means the opposite, and negation means the opposite. So this is going to be equivalent to, well, apply that negation to the inside and switch everything. So this is going to be negation P, the or switches to and then negation Q. And this also works if we have the negation of P and Q. It's going to be equivalent to, well, switch everything. So negation P, and becomes or, and then negation Q. So here we have a couple laws when dealing with equivalent statements and dealing with conditionals and biconditionals. So here is our conditional statement, if P then Q. And this is going to be equivalent to a disjunction in this form, not P or Q. So you can see if you have P arrow Q, you can take the P, or whatever the antecedent is, and negate it, change the conditional arrow into an or a disjunction, and then leave the consequent, or the Q, alone. And this can go forwards and backwards. So you can take this or statement and change it into an if-then by following the same pattern. And then for a biconditional, we looked at this one briefly in a previous section, but P if and only if Q is the same thing as if P then Q and if Q then P. So again, if you see this, it's equivalent to this over here, and if you see this, it's equivalent to this. So we want to practice these skills by transforming the following statements to create equivalent statements. So here, if we have the negation on the outside of parentheses, remember we can basically apply it by changing all of the inside. So the negation applies to P and becomes negation P. The or flips over, becomes and. Then the negation applies to negation Q. And here we have a double negative, which is going to make a positive, so we just have Q. In our next one, here we see P and not Q. So in this case, to make an equivalent statement, we're actually going to take out a negation. Okay, because there's nothing else we can do with the and statement other than this. So we take out the negation, and then we switch everything for the inside. So P becomes negation P, and becomes or, negation Q becomes Q. You can always test it by going backwards to see if we get the same thing. So negation P is P, or switches to and, negation Q is negation Q. All right, in our next example, we have if P, then not Q. So we're actually going to apply this equivalent conditional statement. So we can change a conditional statement into an or statement by negating the first part. So we're going to negate the P and leaving the second part alone. So we're going to leave negation Q as negation Q. All right, in this example here, we can actually do a couple things. Here we have a conditional statement, so we are going to change it first to an or. So we're going to negate this first part. And we're going to leave the second part R. Now here we could actually apply this negation as well. And so we get negation Q or negation P or R. Now parentheses or not, it really doesn't matter because we already showed that it doesn't matter when you're dealing with an or. We can just leave it like this. For our next one, here we have an or. And it wants us to write an equivalent statement, and there's really two ways we can do this. We can change this into a negation, or we can change it into a conditional statement. I want you to go ahead and try this on your own. Change it first into a negation using De Morgan's laws, and then change it also into a conditional statement using this information right up here. Go ahead and pause the video and come on back to check your work. Welcome back. you should have gotten it is false that Q and not P. So you just change everything inside. And then for the conditional, you should have gotten if Q, then P. So you change the first one, you leave the second one, and you change the or to an arrow. And for our last one here, we have a biconditional, so we're going to use this one on the bottom here to rewrite this. So this becomes if not Q, then not P, and if not P, then not Q. There's lots of other ways we could change this, but we're just going to go one step and leave that just like that for now. So what we can do now is select statements that are logically equivalent to each other. So it says the sun is not shining, but it is not raining. And it says let P be the sun is shining and Q be it is raining. So we have 4 statements using the P and Q. The easiest way to do this is to first change everything into symbolic statements. So our original statement, the sun is not shining, but is another word for and, it is not raining. So and it is not raining. And then we're going to change A through D also into symbolic statements. So it is not true that. So that's going to go ahead and start with a negation parentheses. The sun is shining and it is raining. So the sun is shining, P, and it is raining. For B, it is not raining or the sun is not shining. So not Q or not P. For letter C, the sun is shining or it is raining. So the sun is shining or it is raining. And letter D, it is not true that the sun is shining or it is raining. So the next thing I would try to do is, just like in the previous examples, is change this into an equivalent statement. So to see which of these is equivalent to this one, I would go ahead and change these, try to change these into equivalent statements that it become and statements. So here, if we have the negation, we can apply De Morgan's law and get negation P or negation Q. So will or and give you the same truth value? No, they won't. So A is not equivalent. Now here, we could simply rearrange this to say not P or not Q, because order doesn't matter with an or, and you see that A and B are the same thing, so they're not equivalent to the original statement. P or Q? Well, there's no way of changing an or into an and statement here. So that one is not going to be true either. And this last one, if we apply the negation, we get negation P and negation Q, and you'll see that this looks exactly like this. So D is the equivalent statement. Now this can be a little bit tricky. Just try changing them using De Morgan's laws. You could also have tried changing this one. We could change that into a negation. And we could have seen that letter D works right there. And you can also revert to truth tables if you have the time to do that. All right, for example 4, we're going to use De Morgan's laws to write the equivalent statement now. It says the car is too long or the garage is too short. So the car is too long is P, or the garage is too short. So if we want to write an equivalent statement, De Morgan's laws, it takes an or statement and applies a negation. So it would be not P and not Q. So really, we transformed this into symbolic statement, and then we transform this into a negation, and this now we want to transform back into words. So the negation on the outside means it is false that. Okay, then not P. So the car is not too long. And then this symbol is and then not Q. The garage is not too short. Okay, and this would be our equivalent statement right here. All right, I want you to go and try example 5 on your own. Go ahead and translate this into symbols. Use De Morgan's laws to write an equivalent symbolic statement and then transform that back into words. Go ahead and pause the video and come back when you're finished to check your work. All right, welcome back. Go ahead and check your symbolic statements here and your written statement here. And our last example says, write the following as an equivalent biconditional statement. If the figure is a triangle, then the figure has 3 angles. And if the figure has 3 angles, then the figure is a triangle. So here, we're going to let P equal the figure is a triangle. And then we're going to let Q equal the figure has 3 angles. So this statement up here is translated, if the figure is a triangle, then the figure has 3 angles. And if the figure has 3 angles, then the figure is a triangle. So our equivalent statement to this, you can see we have a conditional going one way and a conditional going the other way. So this is a biconditional. So we can rewrite this as being the figure is a triangle if and only if the figure has 3 angles. Now it turns out that most definitions are written using the if and only if. The reason is, well, it's a little bit shorter and it's going to imply that it's a biconditional, that it goes forwards and backwards. So the biconditional definitely is used to shorten things up, and here would be your equivalent statement. All right, that's all for section 3.4a, equivalent logical statements and De Morgan's laws. Go ahead and make sure you try the practice quiz on Milo Studio, and I look forward to seeing all of you back in class. Thanks again for watching.